Hello, and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Today's podcast is going to be about a topic that we've basically been asked the same question several times by three different listeners. And basically, to kind of summarize them, the question has been, why are some electric vehicles more efficient than others? And really the context of that is that one of the key performance indicator, if not the key performance indicator for an electric vehicle, is the achievable range on a given amount of battery capacity. The battery, because that's the most expensive component in the vehicle, so normally it's something like 60% of the materials cost. You know, if you think about even at the $100 per kilowatt hour cell cost, which would translate into about $150 per kilowatt hour finished pack cost, a 100 kilowatt hour pack is still like $15,000, so it's a lot of money, whichever way you cut it. And it really is the most important thing that people look for, I think, when they're buying an EV, is the range that they can have. And in fact, it's one of the reasons why people don't buy an EV at all yet, because they see that they don't quite get as much range as they would like to have out of it. So I think people don't really care how big the battery is. Really what they care about is how far it will get them. So, you know, I don't care if it's a 100 kilowatt hour battery or an 80 kilowatt hour battery. What I care is how far I'm going to get. Can I do 250 miles or 300 miles or 400 miles? That's the most important headline figure. And, you know, the more range that we can get for the smallest possible battery, that's a massive win. If we can get 10% more efficiency out of the vehicle, that means we could take $1,500 out of the cost of the car. And in automotive margin terms, this is absolutely huge. So we've been asked by several listeners, you know, what are the main reasons for the differences in efficiency? Some listeners have asked, why is there a difference in the efficiency figures published between Europe and the USA? And other listeners were particularly interested to know, why is there such a big variation between seemingly similar cars? So why does a Hyundai Ioniq have a published efficiency of 11.5 kilowatt hours per 100 kilometer, whereas a Nissan Leaf, which is, you know, it's a similar size, if not, maybe the Leaf is a little bit of a smaller car, has an published efficiency of 15 kilowatt hours per 100 kilometer. So that means the Ioniq would use 20% less electricity per 100 kilometer than a Leaf. So in theory, the Ioniq would have 20% more range on the same size battery pack, or could have a 20% smaller battery pack but deliver the same range. That's a huge difference. So first of all electric cars have a published efficiency figure, and typically this is expressed in terms of kilowatt hours per 100 kilometer. What this is, it represents the amount of energy that you'd need to travel 100 kilometers. So simply put, if you had an efficiency figure of 20 kilowatt hours per 100 kilometers, you'd be able to go 500 kilometers on a 100 kilowatt hour battery pack. So in Europe and the USA, these official figures are published, but they're obtained in slightly different ways. So the sort of method is the same in principle, that they're obtained by subjecting the car to a standardized driving cycle, but the cycles are different. So we would expect, as we stand now, to always have different figures for the USA and for Europe, standardized vehicle range and efficiency in terms of kilowatt hours per 100 kilometer. In the US, they use the EPA test cycle, and in Europe until recently we used a very gentle driving cycle called the NEDC cycle, and this is actually the same driving cycle that's used to test emissions and fuel consumption on internal combustion engine vehicles. And now, in the same way internal combustion engine vehicles in Europe have moved to a new test cycle, so have EVs. So we now use what's called a WLTP cycle, and that's a much harder driving cycle than the old NEDC. So we've seen the published values get closer between the US EPA cycle and the European WLTP, although the WLTP is a world cycle, but it's used in Europe. And the values are getting much, much closer together. In future, in Europe, when RDE, or real driving environment tests, comes in, this will be used on EVs as well as on the ICE vehicles, and that'll close the gap between the published figures even more. And what it'll also do is, everyone knows when you buy an internal combustion engine vehicle, you never quite get the published miles per gallon out of it, and that's because the test is done in a very controlled way. And even the WLTP test is still done in a very controlled way, in a test lab, at a controlled temperature, on a rolling road. What the RDE tests that are coming in will do is they'll put the car out on the public highway in all sorts of different conditions, at different altitudes, at different ambient temperatures, and that will measure the efficiency of the vehicle. So there's this new RDE test coming in, and that's going to be much harder than even the WLTP test, because the vehicle's got to cope with such a wide range of operating conditions. So it's worth bearing in mind that just like with the petrol and diesel, there's always going to be a gap between the real world performance and the published figures until these RDE figures come along, and then actually really it should be very close. The RDE figures should be very, very close. We'll stick a note. We'll stick a link in the notes below to the actual test cycles, so you can kind of see the actual driving pattern that the cars are put through on both the EPA test and the WLTP test, and take a look at that. So achieving a good result in both of these driving cycle tests is a really, really big deal, because that gives you your headline vehicle range. So you can say my car's going to do 250 miles or 300 miles or whatever. And it's a massive thing for people's buying decisions, because I think the range of EVs is still at the point where, quite a few people are unsure. Maybe they often have to do a trip that's a bit longer. Even, to be honest, people who only do that trip once a year, they still can be unsure even about buying an EV in the first place. And then when people are comparing EVs to EVs, they're comparing that range that they can get out of the vehicle. So it's a really it is a really important thing. But then we have to ask, why is there a difference on that standard test? You've got two cars with the same capacity battery pack. Why is one car getting 15 kilowatt hours per 100 kilometer energy consumption versus the other car getting 11.5 kilowatt hours per 100 kilometer? And basically this comes down to the efficiency of the car and the efficiency of the powertrain. And thinking about this, come out with basically a top 5. So there's 5 main sources of efficiency gains in an electric vehicle. Okay, so the first one is the battery and the charging system. Second one, traction motor and power electronics. Third, the ancillary systems. Fourth, aerodynamics. 5, vehicle weight. So just to go into these in a bit more detail. So for the first one, every testing cycle takes into account the efficiency of the charging process. So they don't just look at the fuel gauge on the dashboard to see what's happened. What the vehicle is charged with a meter, then it's driven through the test cycle, and then it's charged again, but with a meter on the AC side of the battery charger. So the efficiency of the battery charger, as it converts the mains AC electricity into the DC to charge up the battery pack, is really important. And then the losses in the battery pack and the electrical distribution system on the vehicle are also really important. And if we look at a battery charger, there's actually quite a lot in an onboard charger in a vehicle. The onboard charger has to convert the mains AC electricity into DC to be able to charge the battery up. And, the DC that you need to charge the battery, you've got to be able to voltage control it, you've got to be able to current control it. It's quite a complicated affair. And then we also need some really big filters to make sure we don't get any unwanted electrical noise going back onto the local grid and disrupting other things that are plugged in. So what you don't want is you plug in your car to charge and the television switches off in the living room of the house. It's really important. So there's a lot of electronics. It's very complicated inside the onboard charger, and basically several conversion steps that you can break that down into. So first of all, you convert the AC into DC, and this is done normally using something called a PFC boost converter. And then after that, we'd have a secondary DC-DC converter. So once we've done the first step to convert the AC into DC, and we have a controlled DC voltage coming out, we have a secondary step that we have a DC-DC converter, and those two combined mean that we can get output voltage and output current control from the onboard charger. Now, these converters use high voltage switching devices such as IGBTs, and there's also typically diodes and a transformer, inductors and capacitors, and all of these devices have losses associated with their operation. And in fact, for instance, high frequency operation might reduce the loss in the inductors and the transformers, but it would increase switching losses in the IGBTs. So there's trade-offs to make inside the onboard charger and design considerations there. But basically, we want a really efficient onboard charger design with the most efficient devices that we can get, very efficient switching devices. And there's some really exciting new stuff coming through, particularly with silicon carbide switching devices. It's going to help to make onboard chargers that bit more efficient. So that first part of the process will be helped. And then the next bit, once we've got that DC coming out of the onboard charger to charge the battery, we're passing DC current into the battery pack, and there's internal ohmic losses in the battery pack due to the cell internal resistance, and also in the cables and the bus bars used to transmit all the power. So optimizing the layout of the pack and the charger to minimize these losses, optimizing the cell design to minimize losses inside the cell, can really help to deliver some really good gains at that front end, that initial first step in the onboard charger and the battery charging efficiency. So then the next step, when we're driving our electric vehicle around, what we're doing is converting the stored DC energy in the battery pack back to AC again to drive the electric traction motor. So this is done with a device called an inverter. The inverter, again, uses switching devices such as IGBTs or silicon carbide MOSFETs to create a sinusoidal AC electrical output. So it takes that DC and it switches it on and off, passes it through some other components, and we get a nice sinusoidal AC output. And again, we should be able to control the voltage of that and the current, and that allows us to control the torque and the speed of the electric motor, which drives the wheels. So the efficiency in the inverter of creating this AC output, and then in the traction motor in converting the AC electrical input into a torque, are really critical. Also, something that shouldn't be ignored is that the interaction between the inverter and the motor is also critical. Sometimes people get a little bit carried away, they get obsessed with individual component efficiencies, and they forget about the system. So it's possible to have a really efficient motor that on paper, that's the most efficient motor you could possibly buy, but in operation, it causes massive losses in the inverter, so you end up with not a very efficient system. So the optimizing and the pairing between the motor and the inverter are really, really important. Now, the relatively light nature of the NEDC driving cycle really favored motors that had good low load efficiency, but sometimes these machines were often quite inefficient at higher loads seen in the EPA and then the WLTP and then obviously real driving. So, in that case, it could mean that actually we might be over-optimizing for the driving test cycle, but then sacrificing some efficiency in real-world use on the vehicle. And I think as the testing methods change and the RDE test comes in, that will start to disappear. There won't be any kind of benefit in doing specific cycle optimization. They need to be really optimized across its whole operating range, depending on how people were going to actually use the vehicle in practice. So one final thing to think about, with the motor and the inverter, it's not just their ability to efficiently accelerate the vehicle, so to use that electricity to create an AC waveform, to create torque, to accelerate the vehicle. It's also the ability of the motor and the inverter to efficiently slow the vehicle down, to perform regenerative braking, as it's called. And in that case, we're using the motor as a generator. We are creating electricity in the motor from the kinetic energy in the vehicle. We convert that in the inverter into DC to be able to charge the battery pack. So it's the same process as driving, but in reverse. So we're putting DC back into the battery pack. Now, some of this efficiency is related to the function of the devices. Obviously, the more regen braking we can harness, the more we can improve the overall cycle efficiency. But another quite key and sometimes overlooked factor is also very simply the layout of the vehicle. And we've talked about this on a previous podcast in some depth. But if the EV is rear-wheel drive only, it's likely that the regenerative braking is going to have to be quite compromised because of trade-offs for vehicle dynamics. So basically, if you have really strong regen braking on the rear wheels, this can have quite a negative impact on vehicle handling. It can be very unsettling. If you are engaging in a sort of high level of regen braking whilst going into a corner, it'd be a bit like doing a handbrake turn. It's going to unsettle the vehicle. So that's one of the reasons why higher performance EVs tend to have traction motors at the back and also traction motors in the front. So a bit of it is torque limits under vehicle acceleration. So we're sort of traction limited under acceleration. But another bit of it is it's better to do that kind of layout to mean that we can run a stronger level of regen braking and recover more energy under braking in the vehicle. So that's the second, the motor, the inverter, the efficiency of those two devices, and then also a little bit of the layout. So number 3 on the list was ancillary systems. And what do we mean by ancillary systems? So this is things such as powertrain cooling, infotainment, lights, heating, ventilation, air conditioning. These all create an electrical load on the battery. It's sometimes referred to as parasitic loads. And basically because it's not really doing what you want to do, although these things are really important and you can't move the vehicle unless you've got the parasitic loads. So you kind of can't get your motion, which is what you want, without having them. And they can be a really big proportion of the driving cycle energy consumption. So if you think about, an electric car or truck moving in slow traffic, but in really extreme hot or cold weather, we could be using as much power for the HVAC system as we are for traction, and particularly a poorly optimized thermal management system for the vehicle powertrain could be as much as 15% of the energy required to propel the vehicle under some driving cycles. So, there's feed-ins here in the ancillary system efficiency from some of the other elements of the vehicle design. For example, really efficient motors and inverters will need less cooling. So these will give a knock-on benefit in reducing parasitic power consumption. And again, I've mentioned that on previous podcasts, and it's really important and shouldn't be overlooked. Sometimes vehicle engineers can get a bit obsessed with component cost, and we might be doing really well to take loads of component cost out of the inverter, or maybe sacrificing a little bit of efficiency. But then that might mean we're having to add more cost into the system in the thermal management, and we're having a less efficient overall system because we've made some trade-offs in one particular area. So that's really it's really important to remember that. So what we want to be doing is reducing these parasitic loads on the vehicle as much as possible. Some motors also have special oil cooling systems. So this is pumping oil to cool and lubricate the motor. And this does give you a really efficient motor. So like we were talking about before, they've gone and optimized the design of the motor. It's really, really efficient. I've got oil cooling inside the motor. And on paper, that looks great. But then when you take into account the power consumed by pumping the oil in the kind of volumes you need to effectively use oil as a coolant, it does have a really big parasitic load on the vehicle. So it might be having quite a negative impact on efficiency. So whilst you pick that particular motor because it was efficient, actually at system level, it's having a negative impact on the efficiency of the vehicle. On the HVAC system, the standard way of providing heat for the occupants is basically an immersion heater. So it's essentially a tank of water with a heating element in it, and it heats the water glycol coolant up, that's then pumped through heat exchangers to give warm air for the occupants. So this is it's directly using electrical energy. And it's all right, but some manufacturers are moving to heat pumps instead of these conventional immersion heaters to provide warm air for the occupants. And even really simple things like having automated control of the HVAC system so that it's hitting a set temperature rather than just the sort of really basic turn red for hot and blue for cold can make a big difference, because what you don't want is basically the vehicle's running too hot for the occupants or too cold for the occupants. You want it to kind of run a predetermined preset temperature so it can turn the heater on and off as demand as demand requires, or turn the air conditioning system on and off as demand requires. One other area in these ancillary systems it's often overlooked, because to be honest, for an internal combustion engine vehicle it just doesn't matter, is thermal insulation. So on an ICE vehicle, you've got so much waste heat that people just don't even think about thermal insulation. But in an EV, that heat is basically taken straight out of your battery range. So if you're having to generate a lot of heat to keep the occupants warm, then that can have it's got a negative impact on your battery range. So actually the level of thermal insulation in the vehicle, so its ability to basically hold in heat when it's cold outside and to limit solar gain when it's sunny, is much, much more important in an EV. And I've not really seen much done on vehicle design in terms of improving the insulation properties of vehicles, but I do expect this to be one area that we will see a lot more of as time goes by, to make those vehicles a bit more efficient to run. And then, a car is bad enough, but then if you think of something huge like a bus, you've got potential for massive solar gain and heat loss through the floor and the walls of the bus. So it's a bit like insulating your house properly. It has the same sort of benefits. So the fourth area I talked about was aerodynamics. Now, I did mention this on on an earlier podcast where we were looking at the difference between electric and conventional trucks. But it's a really big thing, and the impact of aero shouldn't be underestimated. On a conventional vehicle, on an internal combustion engine vehicle, you've got a great big engine at the front of the car, and you've also got a cooling system for the engine, and the cooling system for an internal combustion engine vehicle requires a lot of airflow. You've got basically a huge amount of heat that you need to get rid of. On an electric vehicle, it's much more efficient, so you've got less heat rejection required, and if you optimize the system design, you can really reduce the amount of airflow that you need. And if you think on an internal combustion engine vehicle, from a styling point of view, for years now, we've basically been building vehicles that look like racing cars. So, internal combustion engine needs a lot of cooling, and needs sort of DTM style or touring style or rally style vehicles. Even a regular Volkswagen Golf, if you look at the front bumper of it, it's got all these fake aggressive grills that give the sort of impression of it being a racing car. So all the air vents to drag air in for the engine, the brakes, and also generating downforce. But this all comes at the expense of aerodynamic drag. So, on an EV, there's a really big opportunity, if we can get over the styling thing, to improve the aerodynamic drag by basically smoothing out the front end of the vehicle. If we make sure it's correctly designed and optimized, because we need so much less airflow through the heat exchangers at the front of the vehicle, there's no combustion engine to work around either. So on a normal combustion engine vehicle, you've got the engine to work around, you've got the pedestrian protection stuff to work around, you've got the big heavy metal lump, you've got to provide space. So you're kind of limited in what you can do at the front of the vehicle because you've got the engine to work about. Now, one of the things that this does mean is if it's an EV that's what we would call a conversion, so like, for example, the Golf EV. So they basically taken a standard Golf and they've crammed an EV driveline into it. Now, that conversion, even if it had been a bit more styled, so like the Nissan Leaf is based on a conventional internal combustion engine Nissan, it can limit the amount of aerodynamic optimization that you can do, because you've got your platforms kind of all set up, particularly for the ICE layout. So there's an argument there which says a dedicated EV design could be more efficient than a non-EV design, and I know there's going to be pluses and minuses on that, but that, in my opinion, the dedicated EV design, you're going to be able to do more with that to optimize the aero, and unless you really took it into account at the initial design stage of the vehicle. And that might be one of the things with the current generation of EV Golf. When that Golf platform was designed, no one was really thinking about EVs. Whereas if you were doing that now and designing a new platform now, you would be natively designing that platform to be internal combustion engine and EV. So you'd probably be quite different on the platform design. So aero's massive, huge impact on efficiency of vehicles, and really something we should take into consideration. And we need to drop all of the racing car style grills and vents and flaps and things that all just add drag. So final area on efficiency is weight. Now this is a really interesting one, because when you think about this, it's basically a combination of all of the other areas. So very simply, a heavy vehicle, and if the battery is one of the biggest weight masses in the vehicle, a heavy battery, a big battery, requires more energy to move it around than a light one. It's simple. If I want to get from A to B, accelerate the vehicle, I'm going to need more energy to accelerate a heavy vehicle than a light vehicle. And even if I can recover some under braking because I'm losing it in system efficiencies, I never get it all back. So the weight of the vehicle is really important. Then we've got the weight of all the powertrain components as well. So basically if we look at the system layout at a system level, all of the cables and interconnection systems, good component layout and device integration can save as much as 25 kilograms in the wiring harness of a regular EV. So imagine what you could do in something like a bus or a truck with good component placement and just a bit of thought in terms of optimizing the mass and the weight in the components and in the system, in the wiring harness, and how these things work together. Now, in a normal vehicle, in reducing weight and improving weight for the vehicle class and performance has always been important. So it's been one of the big things that manufacturers could do to get CO2 down, is by trying to take weight out of the vehicle. Now that's been kind of hampered by the fact that we all want bigger vehicles, and SUVs are more and more popular than they've ever been. So bigger vehicles are more popular than smaller vehicles. But there's like a very well understood benefits to taking weight out, and the OEMs know it right down to if I can save a kilo of weight, that's going to improve my fuel consumption by a certain 0.5% or whatever, and that has a value. So they'll spend money to take weight out. Now this is even more important on an EV, and the reason for that is basically we're adding a lot of weight. So the battery on a typical EV passenger car is going to be between 300 and 500 kilograms. And you've still got inverters and traction motor and onboard charger and all the other components as well. So without the battery, that EV probably still weighs about as much as a conventional ICE car. You stick the battery and you're adding 300, 400, 500 kilograms to the weight of the vehicle. So it's a huge amount of weight to be putting in. Anything that we can do to improve the system efficiency, and then shrink the size and the mass of the battery, or take mass out of the vehicle elsewhere, is really going to be important. And the savings that can be delivered are massive. Now there are batteries on the horizon that could take as much as half the weight of the battery pack out of a typical EV. So that kind of thing coming in. It's not so much increasing the energy density, although it is increasing the energy density, but we're not talking now about adding more batteries. So 100 kilowatt hours, 65 kilowatt hours, that's plenty of battery to have in the vehicle. But if we could take 200 kilograms out of the weight of the vehicle, actually that would make a huge impact in terms of increasing range. So that's going to be a big area that people are going to be looking at, is trying to get the battery weight out. And it's amazing, with a battery, there's so much kind of hidden weight that you just forget about in the design process. You've got all the cells, obviously, and it's obvious, I know how much the cells are, but then you've got the packaging for the cells, you've got the bus bars to connect the cells together with, you've got loads and loads of other components, and before you know it, you've added such a lot of weight to the mass of the basic cells that go into the battery pack. So that's it. That is my kind of top 5 list of the reasons why there are differences in efficiency between different kinds of electric vehicles. You've got the differences in efficiency and optimization, how good people have got and are getting. And I think it's only just the beginning. Obviously, some are a little bit further ahead than others, but it's the battery and the charging system, the traction motor and the power electronics, the ancillary systems, aerodynamics and vehicle weight. And they're all the things that have a massive impact on range and efficiency of the vehicle. And if you're out shopping for an EV, you should be looking for those things. Take that figure per kilowatt hour really seriously. I would say make yourself aware of the condition and the specification the vehicle was in when that was being tested. So you're doubly sure that it was being done in the same controlled way as both of the vehicles you're looking at. So if one had air conditioning installed and the air conditioning was on, did the other one have air conditioning installed and the air conditioning was on, etc. But basically, roughly should have been done the same way, but just make yourself aware of that. If you're not in the market to buy an electric vehicle, but maybe you're involved in the design of electric vehicles, hopefully that gives you some things to think about in terms of system and component level optimization, in terms of how you could be looking to take your powertrain forwards to get more efficiency and better range out of a given size of battery. So, thanks very much for taking the time to listen to us today. I really appreciate it. If you have got any other EV-related questions, please do send them in to us. And what we'll do is we'll pull them together and we will feature your question in a future episode within reason. I had a couple of questions that we couldn't put on air. But, send us your questions and we'll pull them together and put them out in future episodes. Don't forget to subscribe to the channel or hit like. Leave us a rating or a comment, depending on which platform you're on, where you're listening to this. And I really look forward to speaking to you again soon. We've got some really great episodes coming. So that's all. Thanks. Bye for now.